1.4 billion kilometers from Earth, a crew of astronauts is orbiting the most beautiful object in the solar system. They have no fuel to leave, they have no surface to land on, and they have known for years that they are never going home. Not because of an accident, not because of a failure, because of arithmetic. Saturn is not just a far destination. It is the exact point in space where the rocket equation, 7 years of radiation exposure, and a body that has been losing bone density every single month since launch, all converge on the same conclusion simultaneously. The rings beneath their windows are disappearing in real time, shedding 10,000 kilograms of ice into the planet every second. The magnetic field surrounding them is too perfectly aligned to exist under any version of physics we currently teach, and the last message they sent to Earth left the spacecraft 83 minutes ago, which means the people who love them are only now hearing words that were spoken while the situation was already past the point of no return. If you want to understand what those astronauts actually see out there, and why the universe built Saturn in a way that allows arrival, but forecloses return, stay with me, get comfortable, and subscribe if you're new. This one is worth it. Part 1. The mission that already knows the ending. There is a moment, somewhere between the 3rd and 4th year of the journey, when the crew stops looking back. Not because there is nothing to see. Earth is still there, a pale, barely distinguishable point of light among 10,000 others, indistinguishable from a moderately bright star unless you know exactly where to look. They know where to look. They have memorized its position relative to the constellations the same way you might memorize the location of a scar. Not because you have to, but because forgetting feels like a different kind of loss. But somewhere around year 3 or 4, the looking back becomes less frequent. Not out of indifference. Out of something more complicated. A quiet psychological migration that no training manual fully prepares you for, because no human being in the history of our species has ever been far enough from home, that home became a theoretical concept rather than a place you could, in any practical sense, return to. By year 7, Saturn fills the observation window. Not dramatically. Not the way science fiction told you it would. There is no sudden reveal, no moment where you round a corner and there it is. Saturn has been growing for months, almost imperceptibly at first. A bright star that became a disk that became a sphere with a faint halo, a sphere that became the most recognizable shape in the solar system. Those rings tilting and catching light in a way that still, even after 7 years of approach, does not feel entirely real. It looks like a model. It looks like something someone built to hang in a museum. It looks somehow fake in the way that only truly extraordinary real things can look fake when you finally stand in front of them. Inside the spacecraft there is silence. Not the silence of empty rooms or sleeping houses. This is a different quality of silence. The silence of people who have been together for 7 years in a metal container roughly the size of a large apartment, who have exhausted every conversation and still find themselves in this particular moment, without words. 7 years. Think about what 7 years means in human terms. It is longer than most romantic relationships last before a significant transition. It is longer than most people stay in a single job. It is long enough to watch a child go from crawling to reading. It is long enough for a city to change its skyline. 7 years is not a trip. 7 years is a chapter of a life. These people have given a chapter of their lives to reach a place they cannot land on, in a ship that does not have enough fuel to bring them home, with bodies that are no longer the bodies they launched with. And here is the thing that the mission planners knew from the beginning, the thing buried in the engineering documents and the biological projections and the fuel calculations, the thing that everyone involved understood but that nobody said plainly out loud at the press conference. This mission did not fail at Saturn. It failed the moment it launched. That is not a dramatic statement. It is a mathematical one. And to understand what it means, you have to understand what makes Saturn fundamentally different from every destination humanity has ever seriously pointed itself toward. Not just farther, but categorically unreachable in a round-trip sense. The way a waterfall is not just a steep river, but a different physical situation entirely. Start with distance, because distance is where the intuition first breaks down. The Earth and Mars, at their closest approach, sit approximately 55 million kilometers apart. That number sounds enormous. And in everyday human terms it is roughly 143 times the distance from the Earth to the Moon, and the Moon already feels impossibly far away when you stand on a beach and look up at it. But in solar system terms, 55 million kilometers is a neighborhood commute. It is close enough that a radio signal, traveling at the speed of light, makes the trip in roughly 3 minutes. It is close enough that a crewed mission, under current propulsion technology, takes somewhere between 6 and 9 months one way. It is close enough that if something goes wrong, the conversation between the crew and Earth is almost a conversation. A 6-minute round-trip delay is inconvenient, but it is manageable. Mission control can still function as mission control. Now consider Saturn. At its closest approach to Earth, Saturn sits approximately 1.2 billion kilometers away. At its farthest, closer to 1.4 billion. Let those numbers sit next to each other for a moment. 55 million versus 1.2 billion. Saturn is not twice as far as Mars. It is not 5 times as far. It is approximately 22 to 25 times farther than Mars at its nearest point. And that difference is not linear in its consequences. It is exponential. It compounds through every single system that keeps a crewed spacecraft operational. It compounds through the fuel budget, through the communication architecture, through the psychological support systems, through the radiation exposure calculations, through the food and water and oxygen requirements, through the medical contingency plans. Every single constraint of a crewed mission gets multiplied by a factor so large that the mission that results from those multiplications is not recognizable as the same category of thing as a Mars mission. The only spacecraft that has ever successfully reached Saturn and conducted meaningful science, there was Cassini-Huygens, a robotic mission launched in October of 1997 that took 6 years and 10 months to arrive. No biological needs, no psychological support, no food, no water, no medical care, no fuel requirement for a return journey. Cassini was free to take the most efficient route available, using gravity assists from Venus, Earth, and Jupiter to build up speed without burning its own propellant. It arrived at Saturn in 2004, spent 13 years conducting science in the Saturnian system, and ended its mission in September of 2017 by plunging deliberately into Saturn's atmosphere, a controlled destruction chosen specifically to prevent contamination of the moons that might harbour life. Cassini never had to come home. That was not a bug in the mission design, it was the only reason the mission was possible at all. A crewed mission cannot be designed around not coming home. At least that is the assumption everyone brings to the table when the mission is first discussed. The assumption gets complicated very quickly. The journey to Saturn takes, under current or near-future propulsion technology, somewhere between 6 and 7 years one way. Add the time in the Saturnian system, presumably at least a year, possibly 2, to justify the expense and risk of getting there, and add the return journey, another 6 to 7 years, and you're looking at a mission duration of somewhere between 13 and 16 years. There are very few human beings alive who have maintained the same level of physical fitness, cognitive sharpness, and psychological stability for 13 to 16 consecutive years under normal circumstances. You're asking a crew to do it in a metal container, in microgravity, bombarded by radiation, eating processed food, with a communication delay that grows from minutes to hours over the course of the mission, completely isolated from every human relationship they have ever built outside the crew itself. You're asking this of human bodies that were not designed for space. You're asking it of human minds that evolved for savannas and social networks and the quiet psychological comfort of knowing that home is within reach. The communication delay alone changes the fundamental nature of the mission in ways that are difficult to fully appreciate until you sit with them. At Saturn's closest approach to Earth, a radio signal takes approximately 68 minutes to make the one-way trip. At its farthest, approximately 83 minutes. A one-way trip. To have a conversation with mission control, the way Apollo astronauts had conversations with Houston, back and forth, responsive, immediate, you would need to wait between 2 and 3 hours for a round-trip exchange. That is not a conversation. That is exchanging letters. Slow letters. Letters where by the time the response arrives, the situation that prompted the message may have resolved itself, or deteriorated past the point where the response is useful, or changed in ways that make the advice irrelevant. The crew of a Saturn mission is not just far from Earth. They are temporally disconnected from Earth. They exist in a very real sense in a different present tense than the people who sent them. And here is the question that sits underneath all of this. the question that the engineering documents and the mission plans and the press conferences never quite answer directly. What kind of destination allows arrival but guarantees no return? What kind of place is far enough, strange enough, demanding enough of the physics of propulsion and the biology of human endurance and the mathematics of fuel consumption that reaching it and leaving it are not two versions of the same problem, but two entirely different problems, one of which has a solution and one of which does not? Saturn is that kind of place. But to understand why the return is impossible before the mission even launches, you need to understand something that has constrained every rocket ever built, every satellite ever launched, every crewed mission ever flown. You need to understand an equation written in 1897 by a Russian schoolteacher named Konstantin Tsiolkovsky, an equation so fundamental to spaceflight that it has never been superseded, only worked around, and in the case of Saturn, not even that. Part 2. The Math That Closes the Door. Konstantin Tsiolkovsky spent most of his life in a small town called Kaluga, about 190 kilometers southwest of Moscow, working as a mathematics teacher in a local school and spending his evenings thinking about rockets. He was largely self-taught, partly deaf since childhood from a bout of scarlet fever, and almost completely ignored by the scientific establishment during his lifetime. He wrote science fiction novels about space travel. He corresponded with a small number of fellow enthusiasts. He built models. And somewhere in those long evenings in Kaluga, he worked out the mathematics that would define the absolute physical limits of everything humanity ever tries to do in space. The Tsiolkovsky rocket equation, published in 1897, is elegant in the way that truly fundamental things are elegant. Not complicated, but ruthless. What it says, stripped of the mathematics, is this: the amount of fuel a rocket needs to change its velocity depends exponentially on the size of that velocity change. Not linearly, exponentially. Double the velocity change you need, and you do not double the fuel required, you multiply it. Add another velocity change on top of that, and you multiply again. Stack several velocity changes together, which is exactly what a round-trip mission requires, and the fuel mass required grows so large, so fast, that it rapidly outpaces any reasonable definition of a buildable spacecraft. To reach Saturn from Earth, a crewed spacecraft needs to execute several major velocity changes. You need an Earth departure burn to escape Earth's gravity and set yourself on an interplanetary trajectory. You need a Saturn capture burn to slow down enough to enter orbit around Saturn rather than flying past it. You need a departure burn at Saturn to leave the Saturnian system and begin the return journey. And you need an Earth arrival maneuver to slow down and re-enter safely rather than slamming into the atmosphere at interplanetary speeds. Each one of those maneuvers costs fuel, and because of the rocket equation, each additional maneuver does not just add fuel, it multiplies the total fuel required, because you need fuel to carry the fuel you will need later. This is the concept engineers call the tyranny of the rocket equation, and it is not a solvable problem in the way that most engineering problems are solvable. You cannot build your way around it. You cannot optimize your way past it. You can be clever. You can use gravity assists, where a spacecraft swings around a planet and steals a small amount of the planet's orbital momentum, gaining velocity without burning any fuel. But gravity assists take time, sometimes years, and time is one of the things a crewed mission cannot afford in unlimited quantities. Let us put some rough numbers to this, not because the specific figures matter, but because the scale of the problem needs to feel real. A mission to Mars requires a delta V, which is the total velocity change budget, of roughly 3.6 kilometers per second for the Earth departure, roughly about 0.9 for Mars capture, and comparable numbers for the return. The total round-trip delta V for a basic Mars mission is manageable within the performance envelope of current heavy-lift launch vehicles using chemical propulsion, though only barely, and only if you accept a significant transit time and very little margin for error. Mars is at the edge of what chemical rockets can currently do with crew. It is hard. It requires enormous vehicles and careful mission design, and the willingness to launch humans on a trajectory where a failure of any critical system ends the mission catastrophically. But it is within the envelope. Saturn is not within the envelope. The delta V required to reach Saturn, capture into orbit, and then return to Earth is not slightly larger than the Mars figure. It is not twice as large. Using direct trajectories without elaborate gravity assists, which a crewed mission largely cannot use because of the time they add, the total delta V budget for a crewed Saturn round trip is several times larger than the Mars budget. And because of the exponential nature of the rocket equation, several times larger in delta V does not mean several times more fuel. It means fuel requirements that grow until the math produces a result that looks less like an engineering challenge and more like an absurdity. You would need to launch a spacecraft that is, by mass, almost entirely fuel. So predominantly fuel that the crew, the life support, the food, the water, the science equipment, the habitat modules, and the return vehicle itself represent a fraction of the total mass so small that the economics of the mission become incoherent. And here is where it gets worse. Because the payload problem does not stay fixed while the fuel problem grows, it grows too. Every additional mass you put on the spacecraft, every kilogram of food, every litre of water, every medical supply, every spare part, every piece of science equipment, requires more fuel to accelerate. More fuel requires a larger fuel tank. A larger fuel tank is more mass. More mass requires more fuel. This circular relationship, sometimes called the payload fraction problem, means that as you add mass to support a crew over a 7-year mission, you're simultaneously increasing the fuel requirement for the entire mission, which forces you to add more fuel, which adds more mass, which requires more fuel. The cycle collapses the viable payload fraction, the percentage of the spacecraft's total launch mass that is actually crew and cargo rather than propellant, to numbers so small that the mission becomes physically incoherent. The life support requirements alone make this painfully clear. A crew of, say, 6 people over a 14-year round trip needs roughly enough food and water to sustain those 6 people for 14 years. At approximately 2 kilograms of consumables per person per day, a conservative estimate for a minimal diet with some water recycling efficiency, 6 people over 14 years need roughly 30,000 kilograms of consumables. That is 30 metric tons, not counting the recycling systems, not counting the habitat mass, not counting the medical supplies, not counting the scientific instruments, and every one of those 30,000 kilograms requires propellant to accelerate it all the way to Saturn and back. You can improve this. You can build better recycling systems. You can develop more calorie-dense food. You can minimize crew size. You can push the technology of life support closer to perfection. But you cannot eliminate the fundamental problem, which is that human beings require mass to stay alive, and mass in space costs propellant, and propellant is the thing you cannot afford to carry. Nuclear thermal propulsion would help. A nuclear thermal rocket uses a nuclear reactor to heat propellant to extremely high temperatures before expelling it, achieving roughly twice the fuel efficiency of the best chemical rockets. That sounds transformative until you do the math and realize that doubling fuel efficiency, under the rocket equation's exponential logic, does not halve the fuel requirement. It reduces it, but not by enough to make a Saturn round trip viable under any realistic mission architecture. Ion drives are more efficient still. The Dawn spacecraft used an ion drive to orbit both Vesta and Ceres. But ion drives produce thrust so gentle that they take months or years to build up the velocity changes a crewed mission needs, and they cannot generate the high thrust burns required for planetary capture. You need high thrust to slow down quickly enough to enter Saturn orbit. Ion drives cannot provide it. The honest conclusion of the propulsion analysis, the one that the engineering documents arrive at when they stop being optimistic and start being rigorous, is this. The rocket equation does not make a crewed Saturn round trip difficult. It makes it non-viable under any propulsion technology that currently exists or that is credibly near-term, not difficult, not expensive, not at the edge of possibility, non-viable. The math closes the door. But here is the thing about that closed door. It is not even the main obstacle. Because even if someone built a propulsion system that somehow solved the fuel problem, somehow generated the delta V required without the exponential fuel mass penalty, the mission would still face a barrier that no amount of engineering can optimize away. It would face the human body. And the human body, it turns out, has been quietly setting its own countdown clock from the moment of launch. A clock that has nothing to do with rockets or fuel or orbital mechanics, and everything to do with what happens when you take a biological system that evolved over millions of years in the gravitational field and magnetic shielding of Earth, and you remove it from both of those things for 7 years. Part 3. The body starts failing before the ship does. There's a corridor at the Johnson Space Center in Houston, where they keep some of the data from long-duration spaceflight studies, bone density scans, cognitive assessments, cardiovascular measurements, genetic analyses from twin studies. And if you look at the numbers without the surrounding context, without the knowledge that these came from human beings who volunteered for these missions and survived them and went on with their lives, the numbers read less like medical records and more like a description of accelerated aging. The human body in space does not hold steady. It does not maintain itself and wait for conditions to improve. It adapts with brutal efficiency to the environment it currently inhabits, and the environment of deep space is one for which no human body is adapted, or has ever been adapted, or can be made to adapt to without consequence. Begin with radiation, because radiation is where the numbers become most alarming most quickly. On Earth, you are protected by two things: the planet's magnetic field, which deflects the most energetic charged particles from the Sun and from deep space, and the atmosphere, roughly 10 metric tons of air per square meter above your head, which absorbs radiation that gets through the magnetic shield. The combination of these two layers reduces your annual radiation exposure to somewhere around 2 to 3 millisieverts per year under normal circumstances, with some variation depending on altitude and geography. That is a number your body can handle. Evolution has had a long time to develop DNA repair mechanisms calibrated to that level of background exposure. In low Earth orbit, aboard the International Space Station, you are above the atmosphere but still mostly within the Earth's magnetic field. Astronauts there receive roughly 80 to 150 millisieverts per year, significantly more than on the surface, but still within a range that, with careful monitoring and mission duration limits, stays below the thresholds where acute harm becomes likely. Beyond Earth's magnetic field, the situation changes completely. In deep space, beyond the magnetopause, the boundary where Earth's magnetic influence gives way to the interplanetary environment, a spacecraft and its crew are exposed to two primary radiation sources: solar particle events, which are intense bursts of radiation from solar flares and coronal mass ejections, and galactic cosmic rays, which are high-energy particles originating from outside our solar system, accelerated by supernova explosions and other violent astrophysical events. Galactic cosmic rays in particular are almost impossible to shield against because they include particles with energies so high that the shielding material itself, when struck, produces secondary radiation, a shower of new particles created by the collision that can actually increase the dose inside a shielded compartment under some circumstances. The estimated radiation exposure for a crew on transit to Saturn and back runs somewhere between 4,000 and 7,000 millisieverts over the full mission duration. NASA's current career exposure limit for astronauts, calibrated to a 3% increased lifetime risk of fatal cancer, is approximately 1,000 millisieverts for a 50-year-old non-smoking male, one of the highest risk tolerance profiles in the astronaut corps. A Saturn mission delivers 4 to 7 times that limit, not over a career, over a single mission. The health implications of 4,000 to 7,000 millisieverts of deep space radiation exposure are not speculative. They are extrapolated from extensive data on radiation exposure in other contexts, from atomic bomb survivors, from radiation therapy patients, from nuclear accident victims, from high-altitude pilots and frequent flyers who accumulate above-average lifetime doses. At those exposure levels, the increased risk of cancer over the remaining lifetime of the crew is substantial, but cancer, as serious as it is, may not be the most operationally relevant consequence during the mission itself. Research conducted on mice exposed to simulated galactic cosmic ray conditions, research that cannot ethically be conducted on human subjects at those doses, which is itself an indicator of the severity, has shown significant cognitive impairment, including reduced performance on tasks requiring memory, spatial reasoning, and anxiety regulation. The proposed mechanism is damage to the hippocampus and prefrontal cortex, brain regions involved in memory formation and executive function, caused by the passage of high-energy heavy ions through neural tissue. These particles do not just ionize molecules as they pass through, they create narrow tracts of heavily ionized tissue, sometimes described as tiny bullet wounds at the cellular level, that are qualitatively different from the diffuse radiation damage caused by X-rays or gamma rays, and that DNA repair mechanisms are less equipped to handle. For a crew that needs to make complex technical decisions, maintain spacecraft systems, conduct scientific observations, and manage interpersonal dynamics under extreme stress for 7 years, Progressive cognitive impairment is not an acceptable outcome, but it may be an unavoidable one, and radiation is just the beginning. Microgravity, the near weightlessness experienced in a spacecraft in freefall, begins affecting the human body within days of exposure and continues affecting it for as long as the exposure continues. The most well-documented effect is bone loss. Human bones are not static structures. They are continuously being broken down and rebuilt by cells called osteoclasts and osteoblasts, and the balance of this remodeling process is regulated in part by the mechanical stress of gravity. When gravity disappears, the bones that carry weight in a normal gravitational environment, the legs, the hips, the lower spine, no longer receive the mechanical stimulus they need to maintain their density. The osteoclasts continue breaking bone down. The osteoblasts stop rebuilding at the same rate. The result is bone loss of approximately 1 to 2% of bone mineral density per month in the most affected regions, 1 to 2% per month, over 7 years, 84 months, that compounds to a theoretical loss of 60 to 80% of bone density in the most affected regions, a number that would leave any surviving crew member with a skeleton that fractures under stresses that normal human activity would not challenge. Exercise can slow this process. Resistance training, running on specialized treadmills with bungee cord harnesses, has been shown to reduce bone loss in long-duration spaceflight to somewhere around 1% per month. But it cannot stop it, and it requires significant daily time commitment, typically 2 hours per day for ISS crew members, that itself competes with every other demand on the crew's time and energy. The cardiovascular system undergoes its own adaptation to microgravity. On Earth, the heart works against gravity to pump blood from the lower body back up to the chest. In microgravity, that gravitational load disappears, and the fluid distribution of the body shifts toward the upper body and head, a sensation astronauts describe as a persistent feeling of head congestion, like having a mild cold that never goes away. More consequentially, the heart, no longer needing to work as hard to maintain circulation, reduces in mass over time. The cardiac muscle becomes less efficient. The cardiovascular system as a whole becomes less capable. After a long-duration mission, returning crew members have reduced aerobic capacity, orthostatic intolerance, meaning they faint when they stand up, because their cardiovascular system can no longer quickly enough respond to the gravitational demands of standing, and cardiovascular fitness that can take months to years to recover. For a crew returning from Saturn, there is no recovery period during the return transit. They are in microgravity for the 7 years it takes them to get there, then for whatever time they spend in the Saturnian system, then for the 7 years of the return. By the time they re-enter Earth's atmosphere, if they re-enter Earth's atmosphere, their cardiovascular systems are not those of healthy middle-aged adults. They are those of people who have been experiencing an accelerated cardiovascular aging process for 14 years in space. The eyes deserve particular attention because the deterioration of vision in long-duration spaceflight was not anticipated when the medical community first began studying astronaut health, and its mechanism is still not completely understood. Spaceflight-associated neuroocular syndrome, abbreviated SANS, is a condition documented in a significant percentage of astronauts who have spent more than 6 months on the International Space Station. It involves structural changes to the eyes, flattening of the back of the eyeball, swelling of the optic disc, development of wrinkles in the membrane behind the retina, that result in blurred vision, and in some cases long-term visual impairment. The leading hypothesis is that in microgravity, the shift of body fluid toward the head increases the pressure of the cerebrospinal fluid around the optic nerve, and that this increased pressure, sustained over months and years, physically remodels the eye. The eye was designed to function at a specific internal pressure, and when the external pressure from cerebrospinal fluid changes that balance, the eye changes shape to compensate, but not helpfully. For a crew on a 7-year transit to Saturn, SANS is not a theoretical risk. It is, based on current data from the International Space Station, a near certain consequence. The crew will arrive at Saturn with vision that has deteriorated from what it was at launch. They will need to read instrument panels, conduct science, manage spacecraft systems, and communicate with Earth using eyes that are no longer the eyes they were trained with. Now add immune system suppression. In the space environment, the immune system does not function normally. Multiple mechanisms contribute: radiation damage to immune cells, the physiological stress response, disrupted sleep cycles, altered gut microbiome. The practical result, documented on the International Space Station, is that latent viruses that exist in the body in dormant form, suppressed by a normally functioning immune system, begin to reactivate. Herpes simplex viruses, Epstein-Barr virus, varicella zoster virus. These are viruses that the immune system of a healthy person keeps quiet without you ever knowing they are there. In space they wake up, they become detectable in saliva and urine samples, they cause symptoms in some crew members, and in a mission environment where medical care is limited to whatever supplies and knowledge are on the spacecraft. A viral reactivation is a medical event that cannot be easily escalated to a hospital. The proposal to address the biological problems with artificial gravity, rotating the spacecraft or a section of it to create centrifugal force that mimics gravity, is real and worth considering, but it does not resolve the core problem of this mission. It trades one set of problems for another. A rotating habitat large enough to provide meaningful artificial gravity at a rotation rate low enough to avoid causing motion sickness. The threshold is roughly 2 revolutions per minute, needs to have a radius of at least several hundred meters at that rotation rate to produce 1 gravity. The structural mass of a rotating habitat of that size added to the spacecraft feeds directly back into the rocket equation's tyranny. You add mass to protect the crew's biology. The added mass requires more fuel. More fuel increases total launch mass. The mission becomes less viable. You have solved the biological problem by making the propulsion problem worse, and the propulsion problem was already the one that closed the door. The 2 problems do not have separate solutions that can be combined. They are the same problem viewed from 2 different angles. Biology and physics have closed around this mission from opposite directions, and they close at the same time, and the crew is inside when they close. Part 4. The point of no return happens quietly. Nobody will announce it. There will not be a mission controller in Houston standing up from a console and saying, "Officially, the return is no longer possible." There will not be a single moment, a single decision, a single failure that crosses a threshold. The point of no return on a Saturn mission does not arrive like a door slamming. It arrives like a room slowly filling with water. You notice it first around your ankles, and then your knees, and then you realize that you noticed it much earlier than the moment the door closed behind you, and the door closed behind you much earlier than you thought. In the early months of the mission, a return to Earth is genuinely possible. Not easy. You have expended significant propellant to escape Earth's gravity and begin the interplanetary trajectory, and reversing that trajectory is not free, but the fuel margins are still such that a sufficiently serious emergency could justify the delta-V cost of turning around. A catastrophic failure of a critical system, a medical emergency that cannot be managed on board, a discovery that the mission cannot achieve its objectives. In those early months, abort options exist in a real sense. By the midpoint of the transit, somewhere around year 3, the abort options have narrowed substantially. The spacecraft is now closer to Saturn than to Earth. The fuel that has been expended on the outbound journey is gone. The propellant required to decelerate, reverse course, re-accelerate toward Earth, and then decelerate again for Earth capture would require fuel that is no longer available. You cannot turn around because you spent the turning around fuel getting to where you are. You can keep going, or you can stop going, which means continuing to drift on your current trajectory, which leads to Saturn. There is no option 3, and somewhere in that middle period, a second threshold crosses the first, the biological threshold. The crew's bodies have now been in microgravity for 3 years. Their bones have been losing density for 3 years. Their cardiovascular systems have been adapting to a fluid-shifted lower gravity demand state for 3 years. Their eyes may already be showing the early structural changes of SANS. Their radiation exposure has accumulated to somewhere around 1,500 to 2,000 millisieverts, already approaching or exceeding NASA's career limit for low Earth orbit astronauts. Even if the propellant existed to turn around at this point, the question of whether the return journey followed by Earth re-entry and the sudden reimposition of full gravity would be survivable becomes a genuine medical question rather than an assumed yes. Re-entry into Earth's atmosphere involves significant g-forces, typically 3 to 4 g for a capsule-style re-entry, briefly higher during peak deceleration. After 3 years of microgravity, 3 to 4 g is not a nuisance. 3 to 4 g is a serious physiological stress on a cardiovascular system that has deconditoned for 3 years, on bones that have been losing density for 3 years, on a person who may have spent years exercising specifically to be able to handle re-entry, but whose body has adapted to the absence of gravity regardless of those efforts. The return journey, even if the fuel existed, is not just a navigation problem. It is a survival problem. The communication delay adds its own quiet dimension to this transition. In the first months, Mission Control's response time is minutes. Inconvenient, but functional. By the midpoint of the transit, the one-way delay is already close to half an hour, and the round-trip communication lag approaches an hour. By arrival at Saturn, the delays are between 68 and 83 minutes one way. Mission Control is not providing real-time support at that point. They are providing historical record, sending advice that will arrive after the situation has already resolved or deteriorated, receiving reports of events that happened more than an hour before the message was transmitted. The crew of a Saturn mission is not in communication with Earth. They are in correspondence with Earth. The distinction matters enormously when the situation requiring support is urgent. This is something that has no precedent in the history of human spaceflight. Every crewed mission in history, Mercury, Gemini, Apollo, Skylab, the Space Shuttle, the International Space Station, has operated within the Earth-Moon system, where light-speed communication delays are measured in fractions of a second to a few seconds at most. The crew of the International Space Station can call Mission Control the way you call a doctor, the way you describe symptoms and receive a diagnosis, and have someone guide you through a procedure. The crew of a Saturn mission cannot do this. By the time they describe symptoms, Mission Control's response will arrive over an hour later. By the time Mission Control suggests a procedure, the patient's condition will have changed. By the time the crew confirms the outcome, Mission Control will be receiving the description of a procedure they suggested more than 2 hours ago. The crew becomes, by necessity rather than by choice, the sole decision-making authority for every situation that develops on the mission. This is not the intended design of any crewed mission. It is the physical consequence of distance. The people who trained for this mission were trained with the assumption that expertise would always be available, that Mission Control would be a real-time resource, that the institutional knowledge of hundreds of engineers and scientists and doctors back on Earth was always a radio call away. At Saturn, that assumption is false. The expertise that exists on the spacecraft is the only expertise that matters, and if that expertise is insufficient for the situation at hand, no amount of transmission power will provide the answer in time. There is a psychological literature on isolation and confinement that space agencies have studied carefully in preparation for long-duration missions. Antarctic winter-over studies, submarine deployment research, simulated Mars mission studies like the Moscow-based Mars 500 project, where a crew spent 520 days in a sealed habitat to simulate an interplanetary mission. The consistent finding from this research is that human beings can adapt to remarkable degrees of isolation and confinement, but that the adaptation comes at a cost, in mood, in interpersonal relationships, in cognitive performance, in what psychologists call third-quarter phenomenon, a documented tendency for mission performance and crew morale to deteriorate significantly in the final third of a long mission, even when the first 2/3 were managed successfully. On a mission to Saturn, the third quarter begins around year 5, and the crew knows, because they have the training and the intelligence to know, that the deterioration happening in their bodies and the deterioration happening in the mission's return feasibility are running on parallel tracks, converging at the same destination, a point past which returning is not a choice they can make, even if they wanted to. The moment they understand this, and they will understand it because they are the most comprehensively educated humans ever sent to a difficult place, is not a dramatic moment. There is no speech. There is no ceremony. There is perhaps a long silence in the observation module, looking at the growing disk of Saturn, listening to the spacecraft system's hum, aware that the people back on Earth who are tracking their telemetry are receiving data from over an hour ago, that the Earth they left 7 years prior is now a theoretical concept, and that the question that has been quietly present since launch, are we going to make it back, has been answered, somewhere in the last few months or years, without anyone officially noting the moment of the answer. They are not going back, and Saturn is still 3 months away. Part 5. Arrival at a world without a surface. The rings arrive first. Not Saturn, the rings. On the final approach, Saturn's disk is already large enough to resolve clearly. but it is the rings that command attention, because the rings are enormous in a way that no description quite prepares you for. At approximately 280,000 kilometers in total width, wider than the distance from Earth to the Moon, the ring system spans an arc so large that it dominates the view even from distances where Saturn itself is still building in size. From the right angle, with the rings tilted toward you, they catch sunlight and scatter it in bands of white and gold and faint brown that look, absurdly, like the brushstrokes of a painting too large to see all at once. But let the rings recede for a moment, because before they can be understood, Saturn itself needs to be confronted. And Saturn, as a destination, presents a problem so fundamental that it should probably have been the first question anyone asked when the mission was conceived. Saturn is a gas giant. It does not have a solid surface. This requires some unpacking, because the phrase gas giant is familiar enough from school curricula and space documentaries that it can wash over you without fully registering what it means in practical terms. What it means is this: there is no ground, there is no place to land, there is no surface that a spacecraft could approach and set down on. Saturn is, from its outermost cloud tops all the way to its centre, a continuous gradient of increasing pressure and temperature and density, with no boundary layer, no transition from atmosphere to surface, nothing that could meaningfully be called a place to stand. The upper atmosphere of Saturn is mostly hydrogen and helium, the two lightest and most abundant elements in the universe. Descend into it, and the pressure and temperature increase continuously. At a depth of perhaps 200 to 300 kilometers below the visible cloud tops, a modest depth by planetary standards, the pressure reaches the point where hydrogen can no longer exist as a gas. The molecules are squeezed so tightly together that hydrogen transitions into a liquid, though a liquid unlike any liquid on Earth, a liquid under pressures of tens of thousands of atmospheres that behaves more like a fluid metal than like water in a glass. Go deeper, and the pressure continues to build, reaching millions of atmospheres near the core, temperatures of tens of thousands of degrees, a state of matter so extreme that the usual categories of solid, liquid, and gas become inadequate descriptions. A spacecraft entering Saturn's atmosphere would not reach the bottom and find a surface. It would be crushed and vaporized somewhere in the intermediate layers, the precise depth depending on the structural integrity of the spacecraft, with the certainty of destruction increasing with every kilometer of descent. The Galileo probe dropped into Jupiter's atmosphere in 1995, Jupiter being Saturn's larger neighbour and similarly gas-dominated, survived for approximately 58 minutes after entry, before the pressure and temperature exceeded its structural limits. Saturn's atmosphere is somewhat different from Jupiter's, but the outcome for any spacecraft attempting descent would be similar: increasing pressure, increasing temperature, and eventual destruction at a depth still far above the interior's most extreme regions. This is the paradox of Saturn as a destination. It is visible from Earth with the naked eye. It has been photographed in extraordinary detail. It has been orbited by Cassini for 13 years, mapped and measured and analysed to a degree of scientific thoroughness that few objects in the solar system can match, and yet it is, in a fundamental sense, unreachable. You can reach the vicinity of Saturn, you can orbit Saturn, you can observe Saturn from a distance of tens of thousands of kilometers, but you cannot go to Saturn the way you can go to a place, the way you can arrive and stand somewhere and be there. There is nowhere to be. There is no ground beneath the clouds. The place is not a place. It is a gradient. Imagine crossing an ocean only to find that what you thought was a continent is actually a fog bank, that the solid ground you are sailing toward does not exist, that your destination was never a destination in the physical sense you assumed. Now imagine that you discovered this after 7 years of sailing, with no fuel to sail back. That is the crew's situation at Saturn. They have arrived at a world they cannot touch, in a ship that cannot leave, orbiting a gradient. There is a number associated with Saturn that captures this strangeness better than most. Saturn's average density is approximately 0.69 grams per cubic centimetre. The density of water is 1 gram per cubic centimetre. Saturn is less dense than water. If you could find an ocean large enough to hold it, a hypothetical that should make you stop and think about scale for a moment, Saturn would float. The largest planet visible from Earth without a telescope, the planet with a ring system spanning the distance from Earth to the Moon, the planet that has dominated mythology and religion, and the scientific imagination since before recorded history is, in some fundamental physical sense hollow enough to float. But do not let that density figure mislead you into thinking Saturn is light or fragile. The average density is low because the outer layers are gas, and gas takes up a lot of space for its mass. The interior is where the density climbs, where the pressure climbs, where the temperatures reach values that make the surface of the Sun seem, in comparison, approachable. Saturn's low average density is the exterior calm of a system that is extraordinarily violent at its core. The crew in orbit around Saturn cannot see the interior. They see the cloud tops, the banded layers of ammonia ice and ammonium hydrosulfide that give Saturn its characteristic tan and cream coloration, the latitudinal bands of wind that run east and west at speeds reaching 1,800 km per hour near the equator, the occasional storm systems that erupt from the deeper atmosphere and persist for months or years before dissolving. They see the rings, those impossibly thin structures stretching hundreds of thousands of kilometers in every direction. They see the moons, 83 confirmed moons as of the most recent counts, a system so complex that it constitutes its own solar system in miniature, complete with tidally locked moons, resonant orbital patterns, and at least one moon, Enceladus, known to be venting liquid water into space from geysers at its south pole, raising questions about habitability that make it one of the most scientifically interesting objects in the solar system. They see all of this from orbit, through windows on instruments, in data. They see the most visually extraordinary object in the solar system from a distance close enough to fill their vision, but far enough that they will never, under any circumstances, stand on anything associated with it and feel solid ground beneath their feet. They came all this way to orbit a place they can never stand on, and the rings they are looking at, those structures that fill the observation windows and scatter light and look impossibly beautiful from any angle, are disappearing. They have been disappearing since before the first human being ever looked up at the night sky and noticed something strange about that particular bright point of light, and they will continue disappearing long after the last human being looks up at anything at all. Part 6. The rings are dying. In real time. Here is something that the images do not convey, that the textbook diagrams do not convey, that even Cassini's extraordinary photography does not fully prepare you for. The rings, for all their apparent solidity and grandeur, are mostly empty space. If you took all the material in Saturn's ring system and compressed it into a single solid object, you would get a body roughly 100 kilometers across, smaller than many of the asteroids in the asteroid belt, smaller than most of Saturn's smaller moons. The rings appear to be a grand, sweeping structure covering hundreds of thousands of kilometers because the material within them is spread impossibly thin. The main ring system averages somewhere between 10 meters and 1 kilometer in thickness. 1 kilometer of thickness across 280,000 kilometers of width. If you modelled the ring system to the same scale as a standard piece of paper, the paper would need to be roughly the size of a football field to represent the rings at the correct width, and its thickness would represent the ring system accurately. They are, in a very real sense, an illusion of substance. A structure that looks solid from a distance but is, up close, a dispersed collection of particles. 95 to 99% water ice, the rest rocky silicate material, ranging in size from dust grains to boulders tens of meters across, each one orbiting Saturn independently on its own Keplerian trajectory, held in the ring plane by the combined gravitational effects of Saturn and the shepherd moons that patrol the ring edges, and they are falling into Saturn. The mechanism, confirmed definitively by data from Cassini's final orbits in its grand finale mission phase, the orbits it flew between the planet and the inner edge of the rings in the last 5 months before its controlled destruction, is called ring rain. The ring particles are not electrically neutral. They carry electric charges, acquired through ultraviolet radiation from the Sun and through interaction with plasma in Saturn's magnetosphere. Charged particles in a magnetic field do not travel in straight lines. They spiral along magnetic field lines. And Saturn's magnetic field lines, in the inner ring region, connect the ring plane to Saturn's upper atmosphere. So the charged ring particles following those field lines rain down continuously into Saturn's atmosphere, particularly at the latitudes where the magnetic field lines intersect the surface. This ring rain is not a trace phenomenon. Cassini measured its rate, and the data suggested that somewhere between 10,000 and 100,000 kilograms of ring material is falling into Saturn every second, per second. At that rate of loss, and the rate is not constant, varying with solar activity and the season on Saturn, but 10,000 to 100,000 kilograms per second gives you an order of magnitude. The ring system has a finite lifetime. Estimates based on Cassini's measurements put the complete disappearance of the main ring system somewhere between 100 million and 300 million years from now. 300 million years sounds like an enormous span of time, and in human terms it is. It is longer than the dinosaurs existed, longer than multicellular life has been complex, longer than any meaningful sense of history can encompass. But in geological and astronomical terms, 300 million years is not a long time. It is less than 10% of the age of the solar system. The rings are not an ancient, permanent feature of Saturn. They are a transient structure, a temporary arrangement of ice and rock that exists now, that has existed for some fraction of Saturn's 4.5 billion year history, and that will be gone long before the Sun enters its red giant phase and expands to swallow the inner solar system. The rings we see, the rings the crew in orbit is looking at through their observation windows, are not the eternal Saturn. They are a moment in Saturn's history, a brief phase of its evolution, and humanity exists during this phase by coincidence of timing rather than cosmic plan. The age of the rings is its own area of scientific uncertainty and debate. Initial assumptions place the rings at roughly the same age as Saturn itself, 4.5 billion years, as ancient as the solar system. Cassini's data complicated this picture significantly. Analysis of the mass of the rings, the rate of contamination of the ice by infalling meteoritic material, and the rate of ring rain loss all pointed to a ring system that is significantly younger than the planet, perhaps between 10 million and 100 million years old. If the higher estimates are correct, the rings formed during the age of the dinosaurs on Earth. If the lower estimates are correct, they may have formed after the extinction that ended the dinosaurs' reign. The leading hypothesis for the rings' origin is the tidal disruption of a moon that orbited within what is called the Roche limit, the distance from a planet inside which tidal forces overcome the gravitational self-cohesion of a smaller body, tearing it apart rather than allowing it to remain intact. A moon that wandered inside Saturn's Roche limit, whether through gravitational perturbation or orbital decay, would have been pulled apart by tidal forces, its material dispersed into the ring plane, the ice and rock of its interior spread into the thin, wide structure that we now observe. The lost moon has been given an informal name by some researchers, chrysalis, though the evidence for its existence is indirect, inferred from the ring composition and mass and from dynamical modelling rather than from direct observation. The crew orbiting Saturn is looking at the remains of a dead moon. They are looking at a structure that is simultaneously younger than the oldest multicellular life on Earth and already well along in the process of falling into the planet it orbits. They are looking at something that will not exist for much longer in cosmic terms, something that most humans who will ever exist will never see, because by the time the population of the solar system has spread to include Saturn's vicinity in any routine way, the rings will be gone or greatly diminished. They have arrived at exactly the right moment in 4.5 billion years of history to see this, and they will never be able to report back on what it felt like to see it from close up, in any time scale that matters to the people who sent them. Which is one of many reasons why the hexagon rotating silently beneath them, a structure that was not supposed to be able to exist, that has been there for decades since we first observed it, that shows no sign of disappearing anytime soon, deserves its own careful consideration. Part 7. The hexagon that should not exist. Voyager 1 arrived at Saturn in November of 1980, and the images it returned changed what everyone thought they knew about the planet. Cassini would refine and deepen that knowledge over 13 extraordinary years beginning in 2004. But it was the Voyager encounter that first revealed the feature at Saturn's North Pole that has generated more scientific puzzlement per square kilometre than almost anything else in the solar system. A persistent, enormous, near-perfect, six-sided atmospheric polygon that has been rotating around Saturn's North Pole without significant change since the first time we looked at it properly. The hexagon is big, not big in the way that weather systems on Earth are big, not the size of a hurricane or a continent. Big in a way that requires a comparison to appreciate. The hexagon is approximately 30,000 kilometers in diameter. Earth's diameter, at the equator, is 12,756 kilometers. The hexagon at Saturn's north pole is roughly 2.5 times as wide as the entire planet Earth. The crew in orbit is looking at a structure in the cloud tops below them that could contain the whole of the Earth inside it with room to spare. It is also remarkably regular. A geometric shape appearing in a natural fluid environment is not inherently impossible. Hexagonal patterns appear in many natural systems, from honeycomb structures to basalt columns to certain crystalline formations, wherever adjacent units of a fluid or solid minimize surface energy by adopting the most efficient packing geometry. But a hexagonal atmospheric structure in a rapidly rotating gas giant's cloud system, maintaining its shape over decades of observation without meaningful degradation or drift, is a different order of phenomenon. Saturn's atmosphere is not behaving like a quiet crystalline system. It is a chaotic, rapidly rotating fluid, driven by enormous temperature gradients and the planet's fast rotation. Saturn completes a full rotation in roughly 10.5 hours, which is fast enough to produce significant Coriolis effects. In that environment, a structure maintaining near-perfect hexagonal geometry for decades is anomalous in a way that demands explanation. Cassini observed the hexagon through multiple Saturnian seasons. Saturn's year is approximately 29.5 Earth years, and the data it collected revealed layers of strangeness beyond the basic geometry. The hexagon is not a surface feature. It extends vertically, reaching from the visible cloud tops down into the atmosphere for hundreds of kilometers. It also extends upward. There is a second, weaker hexagonal pattern stacked above the main structure in the stratosphere, suggesting that whatever dynamic process creates and maintains the hexagon operates throughout a deep column of atmosphere rather than being confined to a single layer. The hexagon changes colour. In the Cassini images taken early in the mission, the hexagon appears blue, a blue associated with the absence of the photochemical haze that covers most of Saturn, allowing shorter wavelength light to scatter from deeper in the atmosphere and giving that region a distinctly cooler, bluer appearance than the surrounding cloud bands. In later Cassini images, taken during a different Saturnian season, the hexagon had changed from blue to gold, an indication that the photochemical haze had developed inside the hexagon, possibly driven by increased sunlight as Saturn's northern hemisphere moved from winter to spring and summer. The hexagon changed colour in a way that tracked the seasons, which tells you something about its relationship to sunlight and atmospheric chemistry, but does not fully explain why it exists in the first place. The most favoured explanation involves a class of atmospheric waves called Rossby waves, large-scale waves in a rotating fluid, familiar from Earth's atmosphere and oceans, where they influence long-term weather patterns and the behaviour of the jet stream. Laboratory experiments have shown that under the right conditions, a rapidly rotating fluid can spontaneously develop polygonal patterns in certain wave modes, hexagons being one of the shapes that emerge naturally in certain rotation regimes. Simulations of Saturn's atmosphere can reproduce hexagonal patterns under specific parameter choices, so the hexagon is not physically impossible. It falls within the space of things that rotating fluid systems can, in principle, produce. What the models cannot explain, at least not yet, is why the hexagon is so stable. In the laboratory experiments and simulations, polygonal patterns can form but tend to drift, evolve, and eventually dissolve as the system's conditions change. Saturn's hexagon has been observed with minimal change in its geometry since the Voyager encounters of 1980 and 81. That is roughly half a Saturn year of observation without significant structural change. The models that produce hexagonal patterns do not generally produce hexagonal patterns that persist for decades at the same location and intensity. Something about the specific conditions at Saturn's north pole, the depth of the jet stream, the precise rotation rate, the temperature structure of the atmosphere, conspires to stabilize this pattern in a way that is not fully captured by current models. The South Pole has no hexagon. It has a hurricane-like polar vortex, not geometrically unusual, behaving more or less as fluid dynamics would predict for a persistent high-latitude storm. The North Pole has the hexagon. Why this asymmetry exists, why the same planet, with the same basic atmospheric composition and dynamics, produces fundamentally different polar structures at its two poles, is another question to which there is no fully satisfying answer. The crew in orbit is looking at something that has been there since before the first personal computer was manufactured on Earth, that will almost certainly still be there long after the mission is over, that has been explained in broad strokes but not in the specific detail that would let you look at a planet and predict that this feature would be there. Saturn keeps the hexagon's mechanism just out of reach, explainable in category, unexplained in specific, and the magnetic field waiting beneath it is even stranger. Part 8. The planet that looks too perfect. Every planet with a liquid metal interior generates a magnetic field. The mechanism is the same in broad strokes for all of them, electrically conducting fluid in motion, driven by heat flowing from the hot interior to the cooler exterior generates electric currents, and those currents generate a magnetic field. The field is not organized or perfectly shaped. It is the product of turbulent, chaotic fluid motion, and it reflects that chaos. Earth's magnetic field is tilted relative to the planet's rotation axis by approximately 11 degrees. Jupiter's magnetic field is tilted by approximately 10 degrees. Uranus and Neptune have magnetic fields so complex and irregular that they do not resemble simple dipoles at all. They look more like the fields of planets with their magnetic generators churning in particularly chaotic configurations. Saturn's magnetic field is tilted relative to the planet's rotation axis by less than 1 degree. Less than 1 degree. A fraction of the tilts observed in every other planet with a magnetic field in our solar system. This should not be possible. Not because there is a law that forbids it, no law forbids it, but because the mechanism that generates magnetic fields requires, at its theoretical foundation, some asymmetry to function. The dynamo process that converts fluid motion into magnetic field is a self-sustaining process, but a perfectly symmetric system cannot sustain it. A perfectly aligned fluid flow, perfectly symmetric around the rotation axis, would not generate a net magnetic field. Some asymmetry is required for the dynamo to work. Saturn's magnetic field is so nearly perfectly aligned that the asymmetry required to generate and sustain it is, by comparison with every other example we know of, vanishingly small. Current understanding cannot fully explain this. The leading hypothesis involves a layer within Saturn's interior called the helium rain layer, a region where helium, which is slightly denser than hydrogen at Saturn's internal temperatures and pressures, condenses and rains downward in slow droplets, like a planetary scale rain in reverse, falling toward the core rather than upward toward clouds. The helium rain layer is itself real. It is the favoured explanation for why Saturn radiates more heat than it receives from the Sun, a heat that is released as helium rains down through denser hydrogen layers, converting gravitational potential energy into thermal energy. The hypothesis for the magnetic field goes further, proposing that the helium rain layer acts as a filter or screen that smooths out the magnetic irregularities generated in the deeper conducting fluid below, allowing only the most symmetric component of the field to emerge at the surface. The magnetic equivalent of running a turbulent signal through a filter that strips out the noise and allows only the smooth component through. It is an elegant hypothesis. It may be correct, but it is not confirmed. The interior of Saturn is not directly observable. The helium rain layer is inferred from the excess heat, and from theoretical models, not measured directly. Cassini's grand finale orbits, threading the gap between the planet and the rings, measured the magnetic field with extraordinary precision, precise enough to discover that the field is not perfectly aligned but deviates from perfect alignment by a fraction of a degree, too small to have been detected before. But they could not image the interior. They could not measure the helium rain directly. They could not confirm the filtering mechanism. Saturn looks orderly. The magnetic field is almost perfectly symmetric. The hexagon is almost perfectly geometric. The rings are almost perfectly flat and organized. These appearances of order are the exterior of a planet whose interior is running at temperatures and pressures that would instantly destroy any structure or instrument we could send to investigate it. The calm geometry on the outside is a mask over turbulence on the inside. This is not a metaphor. It is a physical description of Saturn's structure, and it is one that the crew orbiting above it, their own bodies in a slow process of physiological deterioration, their fuel gauges reading numbers that preclude any return journey, their communication with Earth delayed by more than an hour in each direction, might find uncomfortably resonant. Part 9. Saturn as an inverse world. Take the three great anomalies of Saturn together, and something interesting emerges from their combination. Not a discovery, not a proof of anything specific, but a pattern that seems to describe what Saturn is, at a level deeper than the individual facts. The rings are temporary but look permanent. They are thin enough to be almost nothing. a handful of material spread across a span wider than the Earth-Moon distance, but they appear, from any reasonable viewing distance, to be one of the most substantial features of the solar system. They are already falling into the planet, atom by atom and grain by grain, but to the naked eye and the camera they look like solid structures, unchanging and eternal. The appearance is stability. The reality is continuous, quiet dissolution. The hexagon is stable, but should not be. A polygon in a turbulent fluid, maintained against all the forces that should erode it, observed for decades without meaningful change while the rest of Saturn's atmosphere swirls and evolves around it. It looks like a geometric truth imposed on a chaotic system. It behaves like an exception to the rules of fluid dynamics as we usually apply them, an exception that the rules can accommodate but that they do not predict. The magnetic field is ordered but should not be. Turbulent fluid motion should produce a turbulent magnetic field, tilted, irregular, reflecting the chaos of its origin. Saturn's dynamo produces, against all expectation, a field so aligned with the rotation axis that it looks like the field of a perfectly symmetric planet rather than the field of a churning, convecting, helium-raining interior. The pattern is this. Saturn presents an exterior of remarkable order, geometry, and symmetry, while concealing an interior of turbulence, chaos, and conditions too extreme for any instrument to survive. It is a planet where the outside lies about the inside, where the first impression, beautiful, ordered, geometrically perfect, is the opposite of the physical truth beneath the clouds. There is a philosophical category for objects that present one face and hide another. We call them deceptive, though that word implies intention that Saturn obviously does not have. We call them complex, which is accurate but insufficient. We might simply say that Saturn, more than any other body in the solar system, is a place where appearances are structured in versions of reality, where the surface calm is made possible precisely by the extreme violence occurring beneath it, where the geometric perfection of the exterior is generated and maintained by the chaotic forces it conceals. Other planets do not work this way. Mars presents a chaotic, impact-scarred, geologically active surface above a largely quiet interior that lost most of its heat billions of years ago. Venus presents a scorching, geologically active surface above an interior that generates it. Earth presents a complex, biologically active surface driven by an interior that provides the heat and the plate tectonics to sustain it. In all these cases, the relationship between exterior and interior is more or less what you would expect. The surface is the product of the interior, wearing its origin on its face. Saturn has inverted this. The calm, geometric, perfectly aligned exterior is not a simple product of the interior. It is a filtered version of it, a smoothed, organized signal extracted from an underlying chaos by processes we only partially understand. The rings are the thinly spread remains of something destroyed. The hexagon is a stable pattern maintained by dynamics we cannot fully model. The magnetic field is a symmetric signal generated by a source that should not produce symmetry. The crew orbiting Saturn has reached not just the farthest destination in human history. They have reached the first destination that systematically contradicts the expectation that deep familiarity and close observation will produce understanding. The closer Cassini got to Saturn, the more questions it raised. The more thoroughly its instruments measured the magnetic field, the hexagon, the ring rain, the atmospheric dynamics, the more it revealed that the simple models were insufficient. Saturn, at close range, becomes stranger, not simpler. It is a planet designed, by physics, not by intention, to resist the kind of understanding that lets you feel you know a place, and the crew has arrived here unable to leave, in bodies that are spending themselves, receiving communications from an Earth that exists 83 light-minutes away in a past they can no longer access. They have arrived at the most perfectly strange place in the solar system, in the most constrained circumstances in the history of human exploration, with the most profound questions surrounding them and the most complete isolation behind them. The strangeness of their situation and the strangeness of Saturn are not separate things. They are the same thing, seen from the outside and from the inside simultaneously. Part 10. The crew's situation mirrors the planet. There is a symmetry between the crew and Saturn that nobody planned and nobody would have chosen, but that is, by this point in the mission, inescapable. And once you see it, you cannot unsee it. Saturn presents an exterior of calm and geometric order. the rings tilting in the light at angles that catch the sun and scatter it into bands of gold and white and faint amber, the hexagon rotating steadily at the North Pole with a patience that suggests permanence, the magnetic field aligned within a fraction of a degree of the rotational axis in a way that looks, from the outside, like the product of careful design rather than chaotic physics. Everything about Saturn's exterior communicates stability, geometry, order. It is the most visually organized object in the solar system. You could look at it for hours and come away with the impression of a system that has reached some kind of equilibrium, some settled state, some arrangement that has found its final form and is simply maintaining it. The interior tells a completely different story. Beneath those organized cloud tops, beneath the hexagonal jet stream and the banded latitudinal winds, the pressure climbs from the tens of atmospheres of the upper atmosphere to the millions of atmospheres of the deep interior in a continuous gradient that permits no landing, no contact, no survival of any structure we could build. The temperatures in the deep interior reach tens of thousands of degrees, hotter than the surface of the sun in a planet we think of as cold because it sits far from the sun's warmth. The helium rains downward through layers of liquid metallic hydrogen in slow drops, converting gravitational potential energy into heat that radiates outward and gives Saturn its excess warmth. The dynamo process generating that near-perfect magnetic field is running on turbulent, chaotic fluid motion that should produce an irregular asymmetric field, and instead, through some filtering mechanism we only partially understand, produces something that looks almost too clean to be real. The exterior appearance of Saturn is maintained by processes that are fundamentally violent and fundamentally hidden. The calm is not the truth. The calm is what the violence looks like from far enough away. The crew presents an exterior of professional composure. They are conducting science. They are maintaining spacecraft systems with the methodical attention to detail that 7 years of this specific work has refined into something close to reflex. They are communicating with Earth, recording observations, transmitting data, composing the personal messages to families that arrive 83 minutes after transmission and receive replies that take another 83 minutes to return, so that every exchange of personal words spans nearly 3 hours of elapsed time and feels less like a conversation and more like finding a letter on a doorstep from someone who wrote it, during a version of the day you no longer quite inhabit. They are managing the interpersonal dynamics of 7 years in close quarters with the same small group of human beings, the negotiations and accommodations and careful maintenance of functional relationships that any group of people requires when they cannot leave each other's company, ever, for years at a time, in a space roughly the size of a large apartment that is also their only protection against a vacuum that would kill them in seconds. From the outside, or from the perspective of the telemetry that mission control is reading on screens 1.4 billion kilometers away, the crew looks like what they were trained to be: competent, professional, functioning. The interior reality is different in ways that the training prepared them to understand intellectually, but not to fully anticipate experientially. The bone density has been declining since the first week of the mission, 1 to 2% per month in the most affected regions. The hips, the lower spine, the weight-bearing bones of the legs that have had no weight to bear for 7 years, because there has been no gravity to generate weight. Exercise has slowed this. 2 hours per day on resistance equipment, running harnesses, loading mechanisms designed to impose mechanical stress on bones that no longer receive it naturally. The exercise has not stopped the loss. After 7 years, the bones that remain are not the bones they launched with. The cardiovascular system has adapted to a fluid distribution that shifted toward the head in the first days of microgravity and never fully shifted back. The heart has reduced in mass, the circulatory efficiency has decreased, the capacity for sustained physical exertion is a fraction of what it was at launch. The eyes carry structural changes that imaging equipment on board has documented and that are permanent. The shape of the eyeball altered by years of elevated cerebrospinal fluid pressure. The optic disc changed in ways that reduce the sharpness of the vision they are using to conduct the most important observations in human history. The radiation exposure has accumulated to levels that the pre-mission briefings described in clinical terms: elevated lifetime cancer risk, potential neurological effects, documented immune suppression, and that now exist not as statistics in a briefing document, but as a physical reality distributed through every cell in every body on the spacecraft. The cognitive systems may be subtly compromised in ways that are genuinely difficult to self-assess. This is perhaps the strangest part of the biological situation. The instrument being used to evaluate the damage is itself potentially part of what has been damaged. You cannot fully audit a system using only that system. The crew can run cognitive tests, reaction time, memory, spatial reasoning, executive function, and compare results to baseline measurements taken before launch. The comparisons are not dramatic. No one has lost the ability to do their job. But subtle changes in cognitive performance are exactly the kind of changes that feel, from the inside, like nothing at all. Because the baseline you're comparing yourself against is your memory of yourself, and memory is one of the things that changes. The external competence of the crew is maintained by training, discipline, and the fundamental human capacity to function despite deterioration. But the deterioration is happening. It has been happening for 7 years, and it is not reversible in any time frame that is relevant to the mission. The mission has no fuel for the return. This is not a contingency plan that was never triggered. It is not a failure of any system or any decision. It was the mathematical consequence of attempting to reach Saturn at all. The rocket equation's verdict, delivered not in a dramatic single moment, but across 7 years of propellant consumption, each burn reducing the margins a little further, each course correction spending a little more of the budget until the budget is gone, and what remains in the tanks is the amount of propellant required to maintain the current orbit and conduct the final mission phases, and nothing more. The crew knows the numbers. They have known the numbers since before launch, in the sense that the mission parameters were never concealed from them, that the propulsion analysis was included in their pre-mission training, that every person who accepted a seat on this spacecraft understood what the fuel budget implied about the return. What they did not know, what nobody who has not been in this position can know, because nobody has ever been in this position, is what those numbers feel like from the inside. What it feels like to look at a fuel gauge and understand that it is not reading the end of propellant, it is reading the end of possibilities, the end of options, the end of the set of futures that contains going home. The concept that best describes their situation is not abandonment, in the sense of being forgotten or discarded. Earth has not forgotten them. Earth is tracking their telemetry with extraordinary care, monitoring every system on the spacecraft, analyzing every data packet that arrives over 83 light minutes of transmission delay, sending communications with the regularity and dedication of people who are paying attention, who have not looked away, who are doing everything within their power to support a mission at a distance, where power runs out very quickly. Families are sending personal messages, scientists are sending questions prompted by the data the crew has already transmitted. Mission Control is sending operational updates, system advisories, encouragement. But Earth cannot help them in any operational sense that matters to their immediate situation. The communication delay makes real-time guidance a physical impossibility. By the time a question arrives and an answer returns, a minimum of 2 hours and 46 minutes has passed, and the situation has moved on without the answer. The distance makes physical rescue not just difficult, but categorically impossible, within any time frame the crew's remaining resources can bridge. The propulsion physics makes resupply a fantasy in the same category as wishing the rocket equation were different. Earth can watch. Earth can listen. Earth can receive the data and preserve it and build upon it for decades. Earth cannot intervene in any way that changes what happens to the people who sent the data. This is what functional abandonment means. Not a failure of care, a failure of physics. The universe does not process the emotional reality of the relationship between this crew and the people who love them. The universe processes the speed of light, and the inverse square law, and the rocket equation, and all three have arrived at the same conclusion. Earth is irrelevant to the crew's immediate circumstances in any practical sense, however relevant it remains in every other sense. What remains when the return is gone and the rescue is impossible, and communication has become the slow exchange of letters across a gap that light itself takes over an hour to cross, is the mission. The scientific purpose that justified every sacrifice this endeavour required, the observations that only proximity can provide, the rings seen from thousands of kilometres rather than billions, the hexagon resolved in detail that no Earth-based telescope or robotic spacecraft has ever achieved, the magnetic field measured from inside the magnetosphere by instruments sensitive enough to detect the filtering mechanism that produces its near-perfect symmetry. The auroral storms at the poles, where charged particles from the solar wind spiral down magnetic field lines and excite atmospheric atoms into luminescence, producing light shows that span distances larger than continents in a world that has no continents. The moons, each one a world in miniature, each one yielding data that will take decades to fully analyse. The mission objective has shifted quietly and without ceremony from what it was framed as at launch. It was always described as go, observe, return, report. Only the return has been removed. The rest continues. And perhaps, the observation was always the whole point. Perhaps the return was the part of the plan that required the most optimism, the most hopeful extrapolation from propulsion capabilities and biological resilience that were never guaranteed, the part that everyone needed to believe in to justify launching at all, but that the physics was never fully committed to supporting. The observation was always the achievable part, the thing that justified everything else, and the observation is what the crew is doing now, in the silence of Saturn orbit, with 7 years of journey behind them, and a communication delay that has already transformed them from explorers reporting to contemporaries into something closer to historians speaking to a future that will receive their words long after the moment of speaking has passed. They are not talking to mission control anymore, not really. They are talking to the record, and the record, it turns out, is exactly what they came here to create. Part 11, the last transmission. When the message leaves the spacecraft, it travels at the speed of light, exactly 299,792,458 meters per second, which is the fastest thing in the universe and in this context, still not fast enough. Think about that for a moment. The fastest thing that physics permits, the speed at which the universe has set its absolute ceiling on information transfer, the speed at which light from the sun takes 8 minutes to reach Earth, the speed at which a radio signal from the moon takes just over a second to arrive, the speed that makes real-time communication feel effortless across every distance humanity has ever previously needed to communicate across. That speed, applied to the distance between Saturn and Earth, produces a one-way travel time of 83 minutes. And 83 minutes, it turns out, is not a communication delay in any sense that the word delay usually implies. It is something categorically different, something that changes the fundamental nature of the relationship between the crew and every human being who is not on that spacecraft. The signal travels outward from the orbit of Saturn, past the ring plane where particles of ice and rock orbit in their thin, wide dispersal, through the interplanetary medium, the sparse plasma and dust and radiation that fills the space between planets, and that is nothing like the vacuum of popular imagination, being instead a tenuous but continuous environment threaded by the sun's magnetic field and populated by the constant outflow of charged particles called the solar wind. The signal passes the orbit of Jupiter, crosses the asteroid belt without interacting with it in any meaningful way, because the asteroid belt is mostly empty space, despite what the movies suggest, passes the orbit of Mars, curves inward toward the Sun following the geometry of the solar system, passes the orbit of Venus, and arrives at Earth approximately 83 minutes after it was transmitted. 83 minutes ago, the crew member who recorded the message was sitting in front of a microphone somewhere in the spacecraft, perhaps in the communications module, perhaps in the observation section, looking at Saturn while speaking about it, describing what they see in real time to people who will not receive that real-time description until it is no longer real time. The words were formed, recorded, encoded, compressed, aimed at a point in space where Earth will be 83 minutes from now. Because you cannot aim a transmission at where Earth is, you have to aim it at where Earth will be, which requires knowing Earth's position with enough precision to hit a target 1.4 billion kilometers away with a radio beam, and transmitted. Now the message arrives at a receiving dish somewhere in a desert, large and white, and pointed at a precise location in the sky, and the people who hear it are receiving a communication from 83 minutes in the past. They are, in a very specific and non-metaphorical sense, hearing the voice of someone who spoke those words in a moment that no longer exists. Think about what 83 minutes means when the situation requires a response, not an abstract response, not a scheduled reply to a routine status update, a response to something urgent. The crew describes something they are observing, a sudden unexpected change in the ring structure that the instruments are flagging as anomalous, an unexplained brightening in the aurora at a location, an intensity that the models did not predict, a reading from a critical spacecraft system that does not match what it should be reading, a medical symptom in a crew member that appeared in the last few hours and is developing in a direction that the onboard medical resources may or may not be adequate to address. The people at the receiving end hear this. They react with the urgency that the description demands. They pull in the relevant specialists, the ring dynamics expert who has been waiting for exactly this kind of observation, the spacecraft systems engineer who knows the subsystem being described in more detail than anyone else alive, the flight surgeon who has been monitoring the crew's medical telemetry for 7 years and who now needs to give advice about a situation unfolding in a body that is 1.4 billion kilometers away. They confer. They argue briefly about the right interpretation and the right response. They agree on an answer. They transmit it. It takes another 83 minutes to arrive. Between the moment the crew member finished describing the situation and the moment the response reaches the spacecraft, a minimum of 2 hours and 46 minutes has passed. In that 2 hours and 46 minutes, the universe has not paused to wait for the conversation to conclude. The anomaly in the rings has either resolved into something explainable or developed into something that requires a different response than the one that was sent. The aurora has changed because auroras do not hold still. The spacecraft system has either stabilized or degraded further along whatever trajectory it was on when the original message was transmitted. The medical symptom has evolved because medical symptoms evolve on the timescale of hours in ways that are clinically significant. The answer that the best minds on Earth crafted based on the best description the crew could provide is arriving into a situation that no longer exists in quite the form it was described. It is an answer to a question that the universe has already partially answered on its own, in the intervening hours, without waiting for mission control. This is not a communication delay. It is important to be precise about this, because calling it a delay implies that it is a solvable inconvenience, a lag that better technology might one day reduce, an engineering problem with a future solution. It is not any of those things. It is a temporal disconnect built into the structure of the universe by the finite speed of light and the enormous distance between Saturn and Earth, and no technology can address it short of a technology that transmits information faster than light, which every experiment ever conducted and every theory ever developed with any experimental support suggests is not possible. The crew and mission control are not experiencing the same present tense. They are operating in different presents separated by almost 3 hours, and every exchange between them is an exchange across time as much as across distance. A conversation not between contemporaries but between a present and a recent past, with each party responding to a version of the other's situation that no longer fully exists by the time the response arrives. For routine communication, the scheduled transmission of science data, the daily status reports, the regular exchange of observations and operational updates that constitute the bulk of communication on any long-duration mission. This temporal disconnect is manageable in a practical sense, even if it is never comfortable in a psychological one. The data arrives delayed. The response to the data arrives delayed. Everyone involved understands the delay and accounts for it in how they structure their expectations and their workflows. It is uncomfortable. It is isolating. It is fundamentally different from any communication experience any human being has had in any other context. But it does not prevent the mission from functioning. For emergencies, it is catastrophic in a way that requires careful thought to fully appreciate. An emergency by definition is a situation that is developing faster than the normal pace of operations, a situation where the gap between action and outcome is measured in minutes or hours rather than days or weeks, where the difference between an intervention made now and an intervention made 3 hours from now is the difference between a recoverable situation and an unrecoverable one. Every emergency medical protocol, every spacecraft contingency procedure, every crisis response framework ever developed assumes that the people with the authority and expertise to guide the response can communicate with the people executing the response in something close to real time. The assumption is so fundamental that it is usually invisible. It is simply the background condition within which emergency response is designed. Remove real-time communication, and the entire architecture of emergency support collapses because the expertise is in one place, and the emergency is in another place, and the gap between them is not bridgeable in the time frame that matters. The crew knows this. They have known it since before launch, in the intellectual sense of having been trained on it, having discussed it in mission planning sessions, having acknowledged it in the pre-mission briefings as one of the defining operational constraints of a Saturn mission. And they have known it for 7 years in the experiential sense, the sense of having lived it, day after day, making decisions without real-time support, handling anomalies and medical situations and interpersonal crises and scientific puzzles with the resources present on the spacecraft, and the archived expertise of mission control, which is a very different thing from the real-time expertise of mission control. They have been making autonomous decisions for so long that the autonomy is no longer a departure from normal operations. It is normal operations. Mission control has become something different from what it was at the beginning of the mission. Not a real-time resource, not a responsive partner in decision-making, a repository of archived wisdom, a library of prior advice, a source of context and the knowledge that somewhere 83 light-minutes away, people are paying attention and caring about the outcome. The caring is real. The help is theoretical. The last transmission, whenever it comes, will carry all of this history in its tone, not panic. Panic requires the belief that panic might produce a change in the situation, and there is no version of the situation that panic can change. Not desperation. Desperation requires the belief that there is something just out of reach that desperation might grasp, and there is nothing out of reach that can be grasped at this distance with these resources. Those emotional states have been present at various points over 7 years. It would be dishonest to suggest otherwise, to suggest that human beings in this situation maintain perfect equanimity at every moment. But those states have been processed by time and distance and the slow, patient work of living with a certainty until the certainty becomes simply the shape of your life rather than a wound in it. What remains after that processing is something quieter, something that sounds, to the people receiving it, like the voice of someone who has made their peace, not with dying necessarily, but with the specific shape that their life has taken, and with the fact that the shape was chosen, was accepted, was lived with full knowledge of what it implied. The tone will be calm, precise, oriented outward toward the people receiving the message, rather than inward toward the person sending it. The message will contain data, almost certainly more data than sentiment, not because sentiment is absent, but because the crew understands what the mission is for, what the transmission represents, what the people who receive it will do with it, and how long they will work with it. Science is the legacy. The data is the justification for everything that was spent to produce it. The years, the health, the distance from everyone they loved, the biological cost accumulated in bones and eyes, and cardiovascular systems and immune cells. All of that was spent to produce observations that only this proximity could provide. Sending those observations back is not separate from the sacrifice. It is the purpose of the sacrifice. The message will describe what they see. The rings, lit by the sun, at the specific angle produced by Saturn's position, in its 29.5-year orbit, at this particular moment in history, the light scattering off ice particles that range from dust grains to house-sized boulders in a structure 10 meters thick and 280,000 kilometers wide. The hexagon, rotating below them with its inscrutable geometric stability, its color at this season, its vertical extent into the stratosphere, the precise boundary where its internal dynamics meet the surrounding flow of the broader atmosphere. The auroras, pulsing at the poles in response to the solar wind's varying pressure against the magnetosphere, lighting up in wavelengths that span from the ultraviolet to the infrared, and that a human eye can only partially perceive without instrument assistance. The moons, Titan with its orange hydrocarbon haze and its methane lakes and its atmosphere thicker than Earth's in terms of surface pressure, the only moon in the solar system that could almost pass for a planet if you did not know better. Enceladus with its tiger stripe fractures and its geysers of liquid water venting into space from an ocean confirmed to exist beneath the ice, an ocean with the chemical ingredients that life as we know it requires. Iapetus with its two-tone surface, one hemisphere dark as asphalt and one bright as fresh snow, the boundary between them sharp enough to see from orbit, the mechanism still generating scientific discussion decades after it was first clearly observed. The message will arrive. It will be received at a dish in a desert, decoded, reconstructed, routed to the scientists and engineers and archivists waiting for it. The science in it will be studied for decades by researchers who will spend careers on specific questions the data raises. It will be cited in papers that will themselves be cited in papers written by people who were children when the mission launched. The textbooks that describe Saturn in 50 years will contain observations from this transmission, and the students reading those textbooks will not think about the transmission itself the way you do not think about the specific moment of observation when you read a fact in a textbook. The data will persist. The data will outlast every person involved in producing and receiving it, the way all good science outlasts the scientists. The crew will not know whether it arrived clearly. They will not know whether the data was received intact or whether some portion of it was lost to interference or transmission error. They will not know whether the personal content, if any was included, reached the specific people it was intended for in a form that conveyed what it was meant to convey. They will transmit, and they will wait, and in 83 minutes the light carrying Earth's acknowledgement will begin its journey outward. But they may not be in a position to wait that long. The situation that prompted the transmission may not permit 83 minutes of waiting, and another 83 on top of that. They are already beyond rescue when they speak. They have been beyond rescue for years. This is not a new development. It is the condition that has defined the mission since the fuel margins crossed the threshold, past which return became impossible. A threshold that was crossed quietly, without ceremony, somewhere in the middle years of the transit when nobody made an announcement because there was no announcement to make, because the transition from theoretically returnable to definitively not was not a moment but a gradient, and gradients do not have ceremony. The transmission is not a call for help. It is not a distress signal. It is a record. It is the carefully assembled documentation that someone was here, that human beings, for the first time in the history of the species, crossed the distance to the 6th planet from the Sun and looked at it from close range and measured it with precision instruments and wrote down what they found and sent that record home. It is proof that the journey happened. It is the point of the journey, expressed in compressed data travelling at the speed of light toward a pale blue dot that the crew can no longer distinguish from the star surrounding it. The notes were the point all along, and the notes are on their way home, even if the people who took them are not. Part 12. The Pale Blue Dot. Reversed. On February 14th, 1990, the Voyager 1 spacecraft was 4 billion miles from the Sun, approximately 40 times farther than the average Earth-Sun distance, when Carl Sagan convinced NASA to turn its camera around and take one final image before the camera was permanently shut down to conserve power. The result was a photograph of Earth from the edge of the solar system, a photograph in which Earth appears as a fraction of a pixel, a pale blue dot suspended in a beam of scattered sunlight, barely distinguishable from the noise in the image. Sagan wrote about that photograph in terms that are among the most frequently cited reflections on human scale and cosmic insignificance ever produced. Every human being who ever lived, he noted, lived on that dot. Every king and peasant, every love and hatred, every civilization and every act of destruction, all on that mote of dust suspended in a sunbeam. The crew orbiting Saturn sees something similar, but the geometry is reversed. From Saturn orbit, Earth is not a pale blue dot. It is smaller than a pale blue dot. It is a pale blue pixel in a frame containing several billion other pixels, and it is not immediately distinguishable unless you know exactly where to look, and even when you know where to look, it does not look like home in any sensory or emotional sense. It looks like a star. It looks like the 1,000th star you have glanced at today while scanning the sky for something specific. The entire history of humanity, every person who has ever looked up at the night sky and wondered whether anything was out there looking back, all of that fits inside a point of light smaller than the period at the end of this sentence. There is a reversal here that goes beyond the visual. When Voyager took the pale blue dot photograph, the question it raised was about humanity's smallness in the cosmos, about the humility appropriate to creatures who live on a point of light in an unremarkable spiral arm of an unremarkable galaxy. When the crew orbiting Saturn looks back at Earth, the question is different. The question is not about smallness. The question is about belonging, about the fact that the only place in the known universe where human beings can exist without elaborate technological life support is that point of light, 83 light minutes away, receding in the viewport while the fuel gauges read empty, and the bodies inside the spacecraft accumulate damage that will never fully reverse. Earth is not just where humanity came from, it is the only place where humanity can be. Not in a sentimental sense, in a physical, biological, thermodynamic sense. The atmospheric composition, the pressure, the temperature range, the gravity, the magnetic shielding, the liquid water, the evolved ecosystem that generates oxygen and regulates climate. These are not coincidences or achievements. They are the product of 4.5 billion years of planetary evolution that produced exactly the conditions under which the biological systems of every human being on the crew were designed to operate. Remove those conditions, and the biological systems begin adapting to their absence, which is another way of saying they begin failing at the task of keeping a person alive and well over the decades of a normal human life. The crew knows this. They have known it since before they launched. The mission planning was explicit about the biological consequences. They accepted those consequences as the cost of reaching the most distant destination in human history. They accepted radiation exposure that would shorten their lives. They accepted bone loss that would require years of rehabilitation if they returned. They accepted cognitive risk. They accepted the immune consequences. They accepted the psychological cost of 7 years in a metal container with the same small group of people, with no private space, no outside perspective, no change of scenery in any meaningful sense. They accepted all of this because Saturn was worth it, and because nobody else was going, and because the opportunity to be the first human beings to see this world from close range, to take the measurements that only proximity can provide, to sit in the observation module and watch the rings catch the light while the hexagon rotates below. That opportunity does not come twice. It did not come twice. It will not come twice for a very long time, if ever. The technical, economic and political conditions required to launch a crewed mission to Saturn may not coincide again for generations. The propulsion advances that could make a round trip viable are not on any near-term development timeline. The biological countermeasures that could protect a crew for 14 years are not mature. The cost and complexity of such a mission exceed anything any space agency or private entity has committed to. The window that opened for this crew, whatever combination of technological development, political will, funding and human ambition produced this mission, may not open again within the lifetimes of anyone currently alive. So the crew looks back at Earth, at the pale, essentially invisible point of light that contains everyone who has ever loved them, everyone who taught them, everyone who prepared them for this, everyone who will receive the data they are transmitting and build upon it for decades, everyone who will read about this mission in the history books and try to understand what it felt like to be here. All of that lives in a point of light smaller than the smallest thing you can see with the naked eye in a field of stars. And they look forward at Saturn, at the rings, losing 10,000 to 100,000 kilograms of material every second, slowly becoming an increasingly thin structure that will eventually be gone, at the hexagon, rotating with its inscrutable geometry, stable in a system that should erode it, maintained by dynamics that are only partially understood, at the magnetic field, almost perfectly aligned, filtering the chaos of the interior into something that looks, from outside, like order, at the cloud tops concealing an interior that crushes and vaporizes at pressures that make all engineering aspiration irrelevant, at the moons, Titan and Enceladus and Iapetus, and the 80 others, each one a world in miniature, each one presenting its own set of questions that will require decades of analysis to begin answering. Here is the thought that sits underneath all of this. We tend to think of exploration as a story of expansion, humanity reaching outward, claiming new ground, extending the range of what is known and accessible, and for most of the history of exploration, that is more or less accurate. New land was found, mapped, settled, incorporated. New knowledge was produced and transmitted back and built upon by subsequent explorers who could go farther because their predecessors had gone as far as they did. The expansion was, in broad terms, cumulative. Each generation of explorers extended the range of the previous one. Saturn breaks this story. Saturn is a destination where the expansion stops, not because we ran out of courage or funding or ambition, but because physics erected a set of constraints so fundamental that they cannot be negotiated away. The rocket equation is not an engineering challenge awaiting a better solution. It is a description of how energy, mass and velocity relate to each other, and no technology changes that description. The biological consequences of radiation and microgravity over multi-year timescales are not engineering failures waiting to be corrected. They are descriptions of what happens to biological systems built for Earth when those systems are removed from Earth's conditions for years. No material advancement makes human beings into creatures that do not require the conditions under which they evolved. Saturn is not where exploration fails. Exploration has not failed here. The crew that reaches Saturn, in whatever future generation first attempts it, will have achieved something extraordinary, will have pushed the range of human presence farther than it has ever been pushed, will have produced science that could not have been produced any other way, will have answered questions about the solar system that no instrument alone can answer. That is not failure. That is the farthest reach of success. But it is also the boundary. The place where the physics of the solar system and the biology of humanity converge on the same answer to the same question. How far can you go and still come home? And the answer, precise and irrevocable, is not this far. The rings will disappear in 100 million years or 300 million years, depending on whose models you believe, and Saturn will continue its orbit without them, a gas giant stripped of its most distinctive feature, unrecognizable to anyone who sees it now and might somehow see it then. The hexagon will eventually change. Nothing in fluid dynamics is truly permanent, though on what timescale and toward what configuration, no current model can say. The magnetic field will evolve as the interior cools over billions of years, though so slowly that no human lifetime or 100 human lifetimes would register the change. And Earth, that pale, essentially invisible point of light from the viewport of a Saturn-orbiting spacecraft, will continue to turn, and its oceans will continue to hold liquid water, and its atmosphere will continue to contain the oxygen that biological systems like the crews require, and the people on it will continue to look up at night and find Saturn among the stars and wonder what it would be like to be there. They should hold that wonder carefully, not because Saturn is dangerous, though it is, not because the mission is one way, though it is, but because the wonder itself is something fragile, a product of distance and imagination that is available to anyone who looks up on a clear night, and that would not be available at all if the universe were different, if Saturn did not exist in exactly the orbit it occupies, if the geometry of the solar system did not put it far enough away to be mysterious, but close enough to be visible. We're inside a narrow window. The rings are temporary. The hexagon is, in cosmic terms, recent. Saturn itself is middle-aged by stellar standards, and its current configuration, ringed, hexagonal, polar, too perfect magnetic, is specific to this period in its evolution. The crew that reaches it, whenever that crew launches, will arrive during the specific window when all these features coexist, when the rings have not yet fallen into the planet, when the hexagon has not yet evolved into something else, when the magnetic field still presents its anomalous near perfection. That is not coincidence. It is the nature of exploration. You arrive where you arrive, when you arrive, and the world you find is the world that exists at that moment rather than the world that existed before you got there, or the world that will exist after you leave. The crew orbiting Saturn is seeing Saturn as it is now, in the 21st century of human civilization, in the 4.5 billionth year of Saturn's existence. They are witnesses to a specific moment in the history of a world they cannot land on, in a ship they cannot fly home, in bodies that have been spending themselves since they left. They are not pioneers in the sense of opening a route that others will follow. They are something rarer and more final than pioneers. They are the people who reached the boundary and looked past it and described what they saw, and then they were the boundary itself, the farthest extent of what humanity has been able to reach, the mark at the edge of the map beyond which the territory is known only from remote observation and theoretical extrapolation. Beyond Saturn, the solar system continues. Uranus, Neptune, the Kuiper Belt, the scattered disk, the Oort cloud, the vast and essentially empty space between our Sun and the nearest other star. 4 light-years of nothing at the nearest point, a distance so large that the concepts we have been using in this discussion become inadequate to contain it. The travel time to the nearest star under any current or conceivable near-future propulsion technology is not years. It is not decades. It is thousands of years, tens of thousands of years, geological timescales. The boundary marked by Saturn is not the edge of the solar system. It is the edge of human reach within the solar system, the point past which the solar system is explorable only by our instruments and our mathematics, never by our presence. The crew in orbit looks at the pale blue dot that is Earth and understands something that is very difficult to understand without being exactly where they are, in exactly their situation. Earth is not a limitation. Earth is not the small place you left behind on your way somewhere bigger and more significant. Earth is the place that made you possible, in every sense of the word, biologically, evolutionarily, culturally, personally. Every person who has ever existed, every idea that has ever been thought, every act of love or violence or creation or discovery, every moment of consciousness that has ever occurred in the known universe occurred on or very near that pale blue dot. And the crew is the farthest any of it has ever gotten from home. They will not get farther. Nobody, for a very long time, will get farther. The physics will not change. The rocket equation will not relent. The human body will not evolve fast enough to survive what this journey requires. The pale blue dot will remain the centre of everything, not because the universe arranged it that way, but because the universe did not arrange it any other way, and we go as far as the arrangement allows, and we stop where the arrangement ends. Saturn is not the beginning of our reach into the cosmos. Saturn is the end of it for now, and probably for longer than now, and possibly for a very long time indeed. The rings are beautiful. Look at them while they last.